Okay, to save you some time, I went ahead and worked out for example number 2, I'm given that f of x equals x to the fourth minus 4x cubed. Well, I went ahead and worked out f prime and f double prime. So f prime is 4x to the third minus 12x squared, and f double prime is 12x squared minus 24x, which solves, when you solve, you get your points of inflection to be x equals 0 and x equals 2. Now, I'm going to highlight those there, and I'm going to highlight those there, but I'm also going to highlight them right here on the graph. See right there? Point of inflection and the point of inflection. Right here at this point is when the concavity changes from graphing upward to concave downward. And then here, it's concave upward the rest of the way. Now, how do we tell? Well, we have our 3 intervals. We got 0 and 2. And then we come up with test values in between. I just chose x equals -1. This is already done for you. But if you plug in -1, you will see where f double prime of -1 is greater than 0, which means it's positive. So therefore, it is concave upward. All right, so, and then I'm going to show right there, it is concave upward. Now, if I plug in 1, because it's between 0 and 2, it's going to be f prime is less than 0. So that means it's going to be concave downward, which if you check the graph, that is the case. And then once again, f double prime of 3, because that's my test value. And then from there on out, it is upward as well. So the blue means it's concave upward. The green means it's concave downward, and that's how you can check it. And remember, you don't have to plug in. You don't have to plug in the numbers. If you just want to type this a function on your calculator and then use the table function, I would suggest doing that. Just going to make things a little bit easier for you. All right. Now, with that being said, I want you to look at the following. The converse of theorem is not always true. There's a possibility that the second derivative to be 0 at a point that is not a point of inflection. So in this particular example right here, when f of x equals x to the fourth, as shown in the figure, the second derivative is x equals 0, but at the point 0, 0 is not a point of inflection. So right there, even though f double prime does equal 0, it's not a point of inflection because it stays concave upward. So because the graph is concave upward on both intervals, then f double prime of 0 is not a point of inflection because the concavity has to change from upward to downward or downward to upward. Either way, it has to change in order for it to be a point of inflection. Okay, for this one, I went ahead and I wrote out what f prime of x and f double prime of x are. If f of x equals x squared plus 1 times x over x squared minus 4, you get f prime of x to be -10x all over x squared minus 4 squared. And then f double prime ends up being 10 times 3x squared plus 4 all over x squared minus 4 to the third, and that's using some algebra, but also using the quotient rule. Okay, what we get are points of inflection at 2 and -2. So our intervals from -2 to negative infinity to -2. We use a test interval at 3, and f double prime of -3 is greater than 0, so therefore it's concave upward. And you can check this on your own using your graphing calculator. And then same thing goes from -2 to +2. I use x equals 0, so f double prime of 0 is less than 0, so therefore it is concave downward. And then finally, from 2 to infinity means that x equals 3, so f double prime of 3 is greater than 0, which means that it is concave upward. So concave up. All right, now, for the next one, it's pretty quick, so you just need to know that f double prime of x equals, in this case it equals 4x to the third minus 12x squared, and f prime, or f, that is f prime, sorry, and f double prime is going to be 12x squared minus 24x, which ends up giving us 12x times x minus 2, which means our x values are 0 and 2. You do the same thing here, and you can see the results. From negative infinity to 0, it is f prime is greater than 0, so therefore it's concave upward. From 0 to 2, it is f prime is negative, so it's concave downward. And then finally, f prime, or f, from 2 to infinity, f double prime of that is greater than 0, so therefore it is concave upward. Okay, the next thing we're going to talk about is the second derivative test. Now, here's how the second derivative test works. Let f be a function such that f prime of c equals 0, and the second derivative test exists on an open interval. Here's what it says. We determine our critical numbers. So we determine our critical numbers. Now, if a critical number is plugged into f double prime and is greater than 0, then that means that at that point it is the relative maximum. And if f double prime of c is less than 0, then that's considered a relative maximum. So here's what I did. I got f of x equals negative 3x to the fifth plus 5x to the third. I derived it and got negative 15x to the fourth plus 15x squared. Now, when I solve that, I get my three critical values are x equals 0, x equals 1, and x equals negative 1. So those are my critical numbers. Well, what I do then is I do the second derivative. So I do the second derivative, and I get negative 60x to the third plus 30x. And then I plug each of these numbers into my second derivative. I'm taking the critical numbers from the first derivative and plugging them into the second derivative. Now, in the case of this, f of negative 1 is equal to 30. Now, that in itself is greater than 0. So since it's greater than 0, then that's the relative, then that means that's the relative minimum at x equals negative 1. And you can check that by graphing it on your graph. And since f double prime of 1 is less than 0, then that means that that is the relative maximum. Now, f double prime of 0 is just 0, so it doesn't work there. So here we got the relative maximum when f double prime is less than 0, and when f double prime is greater than 0, then that is our relative minimum. Now let's look at the last part right here. I've tried to cut out some stuff for you so that you can see. Now it says identify where f has a relative minimum. So you got to look for where f prime of x goes from negative to positive. Well, if we look here, it goes from negative to positive at x equals 3. So right there, f prime is negative, and here f prime is 0 or positive. So therefore, x equals 3 is our relative minimum. On the other hand, where f has a relative maximum, in this case, is where f prime goes from positive to negative. So it's at negative x equals negative 1. So that's what you got to look for. Now, identify all the values where f has a point of inflection. Now remember, point of inflection is when f double prime of x is equal to 0 or it does not exist. Well, if we look here at x equals 1, f double prime equals 0, and here f double prime does not exist. So that means that our points of inflection are at x equals 1 and also x equals 7. All right, now here's the last thing we're going to cover. It says write the equation of the line tangent to the curve at y equals f of x at x equals 5. Okay, so here's what we need. f of 5, and we need f prime of 5. Here's why. Okay, so f of 5 equals 3. So that means it's going to be at the point 5, 3. So we know that point. And f prime of 5 is equal to 2, and that's the slope. So m equals 2. So we got our point and we have our slope. So we got the equation y minus y1 equals m times x minus x1. Now remember, the point is y minus 3 equals the slope, which is 2 times x minus 5. Now the reason 2 is the slope is because at f prime of 5, our slope is 2. And the reason why our y value is 3 because f of 5 is 3. So we got that, and you can actually leave it just like that. You can rewrite that in other forms if you want, but you don't have to. So, all right. Please be sure to ask any questions if you have, or if you're virtual students, make sure you email me, and we'll talk more about chapter or section 3-4 in class or on Google Meets. And don't forget, HQ 3-4 is due on Friday.